Hello my physics students, this is Mrs. Buchanan again, and this is flip video number 8. We're going to continue our discussion of Newton's second law of motion, force and acceleration. Let's revisit our big idea. An object accelerates when a net force acts on it. Our learning objective number 3 is discuss the relationship between acceleration and net force. I believe that we need to go back and have a discussion over motion, speed, velocity, and acceleration before that we can show this relationship. More than 2,000 years ago, the ancient Greek scientists were familiar with some of the ideas of physics that we study today. They had a good understanding of some of the properties of light, but they were confused about motion. Great progress in understanding motion occurred with Galileo, and as we discussed in earlier chapters, we talked about his study of balls rolling on inclined planes. So motion is relative. Everything moves. Even things that appear to be at rest move. They move with respect to the sun and stars. When we describe the motion of one object with respect to another, we say that the object is moving relative to another object. A book that is at rest relative to the table it lies on is moving at about 30 kilometers per second relative to the sun. The book moves even faster relative to the center of our galaxy. When we discuss the motion of something, we would describe its motion as relative to something else. An object is moving if its position relative to a fixed point is changing. When we say that a space shuttle moves at 8 kilometers per second, we mean its movement relative to Earth below. When we say a racing car in the Indy 500 reaches a speed of 300 kilometers per hour, of course we mean relative to the track. Unless otherwise stated, when we discuss the speeds of things in our environment, we mean speed with respect to the surface of the Earth, even though the Earth moves around the sun. Motion is relative. When we talk about speed, before the time of Galileo, people described moving things as simply slow or fast. Such descriptions were vague. Galileo is credited as being the first to measure speed by considering the distance covered and the time it takes. Speed is how fast an object is moving. You can calculate the speed of an object by dividing the distance covered by time. For example, if a cheetah covers 50 meters in a time of 2 seconds, its speed is 25 meters per second. Any combination of units for distance and time that are useful and convenient are legitimate for describing speed. Miles per hour, kilometers per hour, centimeters per day, or light years per century are all legitimate units for speed. So let's talk about different types of speed. We actually have two kinds. Instantaneous speed. A car does not always move at the same speed. A car may travel down a street at 50 kilometers per hour, slow to 0 kilometers per hour at a red light, and speed up to only 30 kilometers per hour because of traffic. You can tell the speed of the car at any instant by looking at the car's speedometer. The speed at any instant is called instantaneous speed. A car traveling at 50 kilometers per hour may go that speed for 1 minute. If the car continued at that speed for a full hour, it would cover 50 kilometers. If it continued at that speed for only half an hour, it would cover only half that distance, or 25 kilometers. In 1 minute, the car would cover less than 1 kilometer. Average speed. In planning a trip by car, the driver wants to know how long it will take to cover a certain distance. The car will certainly not travel at the same speed all during the trip. The driver only cares about the average speed for the trip as a whole. The average speed is the total distance covered divided by the time. Average speed can be calculated rather easily. For example, if we drive a distance of 60 kilometers during a time of 1 hour, we say our average speed is 60 kilometers per hour, or if we travel 240 kilometers in 4 hours. Since the average speed is the distance covered divided by the time of travel, it does not indicate variations in speed that may take place during the trip. So in practice, we experience a variety of speeds on most trips, so the average speed is often quite different from the instantaneous speed. Whether we talk about average speed or instantaneous speed, we are talking about the rates at which distance is traveled. If we know average speed and travel time, the distance traveled is easy to find. A simple rearrangement of the definition gives us, for example, total distance covered equals average speed times travel time. For example, if your average speed is 80 kilometers per hour on a 4-hour trip, then you can cover a total distance of 320 kilometers. Velocity. In everyday language, we can use the words speed and velocity interchangeably. In physics, we make a distinction between the two. Very simply, the difference is that velocity is speed in a given direction. When we say a car travels at 60 kilometers per hour, we are specifying its speed. But if we say a car moves at 60 kilometers per hour to the north, we're specifying its velocity. Speed is a description of how fast an object moves. Velocity is how fast and in what direction it moves. So, a quantity such as velocity that simplifies direction as well as magnitude, it is a vector quantity. Speed is scalar. Velocity is a vector quantity. So we talk about two types of velocity. Constant velocity. Constant speed means steady speed. Something with constant speed doesn't speed up or slow down. Constant velocity, on the other hand, means both constant speed and constant direction. Constant direction is in a straight line. The object's path does not curve. So constant velocity means motion in a straight line at a constant speed. So a car going into a circle may have a constant speed, but its velocity is changing. Changing velocity. If either the speed or the direction or both is changing, then the velocity is changing. Constant speed and constant velocity are not the same. A body may move at a constant speed along a curved path, for example, but it does not move with constant velocity because its direction is changing every instant. In a car, there are three controls that are used to change the velocity. One is the gas pedal, which is used to maintain or increase the speed. The second is the brake, which is used to decrease the speed. And the third is the steering wheel, which is used to change direction. And this diagram here shows you the difference between speed and velocity. Speed, when we look at, it's rate at which something moves. How fast, distance over time. We have instantaneous speed and average speed. It's a scalar quantity because it's magnitude only and can be represented as kilometers per hour or meters per second. Velocity, on the other hand, is rate and direction of which something moves. How fast in a specified direction. Constant velocity, changing velocity are the two kinds. It is a vector quantity, magnitude and direction, and it's kilometers per hour with a direction. For example, north or northeast or southwest. Make sure that you understand the difference between the two. So let's talk about acceleration. We can change the state of motion of an object by changing its speed, its direction of motion, or both. Any of these changes is a change in velocity. Sometimes we're interested in how fast the velocity is changing. A driver on a two-lane road who wants to pass another car would like to be able to speed up and pass in the shortest amount of time. Acceleration is the rate at which velocity is changing. You can calculate the acceleration of an object by dividing the change in its velocity by time. So let's go back to our automobile. The driver depresses the gas pedal, which is appropriately called the accelerator. The passengers then experience acceleration, or pickup as it's sometimes called, as they are pressed into their seats. The key idea that defines acceleration is change. Whenever we change our state of motion, we are accelerating. A car that can accelerate well has the ability to change its velocity rapidly. A car that can go from 0 to 60 kilometers per hour in 5 seconds has a greater acceleration than another car that can go from 0 to 80 kilometers per hour in 10 seconds. So having good acceleration means being able to change velocity quickly and does not necessarily refer to how fast something is moving. In physics, the term acceleration applies to decreases as well as increases in speed. The brakes of the car can produce large retarding accelerations, that is, they often produce a large decrease per second in speed. This is called deceleration. We experience deceleration when the driver of a bus or a car slams on the brakes and we tend to hurtle forward. So acceleration is a change in direction. Acceleration is the rate of change in velocity. It is a vector quantity. The effects of acceleration are felt when a car rounds a curve at a constant speed, then your body tends to move toward the outside of the curve. When you accelerate at an angle to your velocity, then your direction changes. So if we have a change in speed, then there's no change in direction and is expressed as the rate at which speed changes. Acceleration in a straight line is change in speed over the time interval. Acceleration, kilometers per hour second. Acceleration is a unit of time that appears twice because it's the unit of speed, kilometers per hour, and the interval of time at which the speed is changing, which is seconds. So let's talk a little bit about how force causes acceleration. When we talk about an unbalanced force, it's acting on an object and it causes that object to accelerate. So it's something that acts on an object. It can be humans or animals that are acting on that object. Gravity and air resistance can also act on it. The net force is the combination of forces acting on an object. Acceleration depends on that net force. To increase acceleration, net force must be increased. Double the net force, the acceleration doubles. To decrease acceleration, the net force must be decreased. An object's acceleration is directly proportional to the net force acting upon it. Thank you very much.